The objective of this video is to determine the voltage induced in a coil side and use this to construct the star of slots. What we're going to do is we're going to go back to our fundamentals for the definition of EMF, and we're going to derive an expression for the EMF, or the voltage that's induced in each slot of our stator. And then we're going to use this derivation to construct a phasor diagram that maps the slots of our stator to the voltage that you would observe in a conductor placed within each slot. And remember that a coil is composed of two coil sides. Each coil side is located within a slot. So our goal here is to try to figure out the transient voltage waveform that we're going to see in each coil side, and this is a step towards designing a coil. We need to figure out which two coil sides to connect to create a coil. And this lecture builds up the star of slots, which is a tool that we use to make these decisions. Let's get started back with the definition of EMF. EMF is defined as the force per unit charge. That's a fundamental definition for voltage, or EMF. And if you recall, back when we introduced Maxwell's equations, we talked about the Lorentz force law as having the following form. And so this equation gives us the force that acts on a charge, a differential charge that we've indicated as dq, in terms of the electric field and the velocity of the charge crossed with the magnetic field. And we'll be ignoring the electric field. We're going to assume it's zero. That's the same as neglecting resistive voltage drop. And so if we were to consider just a single conductor being cut by the field produced from our moving rotor, we'd have a situation that looks kind of like this. Our mission is to figure out how much voltage is induced in that conductor as the pole face of our rotor moves counterclockwise in front of it. Remember, the pole face of our rotor is carrying a magnetic field. And we're going to do that by integrating our force per unit charge. So we'll figure out this voltage by integrating along this length here. And let's back up and consider a simpler example before we tackle the case of a rotating electric machine. Suppose that you are pulling this coil from left to right with velocity v indicated in the diagram. There's a magnetic field present, which is going directly vertically. It's perfectly linking the coil. It's going right into the cross section of the coil. And your mission is to figure out the EMF induced in each branch of this coil. And so we'll do that by using this expression that we wrote out above. And we have to evaluate that cross product. And so the first term, the velocity term, pertains to the differential charges that we have. And at first it seems like there is no charge. However, you have to realize that this is a conductor, and so when we pull our coil from left to right, we're pulling electrons along with us. So there are, in fact, charges located within this conductive surface that can move, that are moving. And so v, the velocity v, is the vector of the conductor. It's the velocity vector of the conductor. And dl is going to be the path that we would take around this loop. So in the first limb over here, dl is facing horizontally, whereas in these limbs, dl is orthogonal to the field. And if we look at this, we can see that because of the nature of the cross product, we have no EMF induced on the horizontal limbs. The only place we can possibly have EMF induced is right here. That's because our field is coming straight up into the coil, and V cross B, you have to use your right-hand rule to see this, will only produce components along these directions. And so we can sketch a voltage source here, which is our EMF. And note that the EMF is in fact going to be equal to our velocity times our magnetic field at x1 times the length of our coil. That's this distance here. Not the length of the coil, but the length of the coil side. And we got this polarity by using our right-hand rule with that integral, with the force integral. So we gathered our polarity from saying V cross B. And we can do the same thing on the right side. And now we have a back EMF of the same expression, but B is evaluated at x2. And so we can see that B of x2 is greater than B of x1, and that is going to cause a current to take this path here. We have a net EMF forcing the current to flow clockwise. And this makes sense. Again, if you go back to your right-hand rule and you see the direction of field that's going to be produced by that current in red, it's going to oppose the change of our magnetic field. It's going to oppose the change of the total flux linking our coil. This is the exact expectation that we should have from our previous discussions about EMF opposing changes in flux. And for completeness, we can again sketch this for our B field now decreasing instead of increasing. So say that we get a little bit further along here, and we have our coil further to the right. And in this case, B of x3 is larger than B of x4. So this voltage source here is larger than this other voltage source, and we're going to get a current that flows the opposite direction. We'll have a current taking this path. And again, this current is flowing so as to oppose any change of flux linking the coil. All right, that's great. Now let's talk about electric motors. In AC machines, our coils are stationary, but our field moves. Our field rotates counterclockwise, the way we've defined this. And so this would be the same thing as saying that our field is stationary, but our coils are rotating clockwise. So it's the relative motion that counts. So I've sketched a 3D view of a motor, or part of a motor. We've got the rotor, it's a salient pole rotor, and then I've shown a conductor in slots 1 through 5, and I've numbered them. So you can see that first we've got a conductor over here in slot 1, and then further over on the stator we have a second conductor in slot 2, and then a conductor in slot 3, 4, 5, and you can imagine this wrapping all the way around the machine. And each of these brown conductors is representative of a coil side placed into one slot. And our goal here is to calculate the voltage that's induced in that coil side. And we're going to do that by evaluating the integral of negative V cross B within the coil from point A to point B. So point B is node B, point A is node A. And we can start by noting that our field is traveling at a certain linear velocity, which is given by the radius of our rotor times the mechanical rotational speed. And the direction that's traveling is in the circumferential direction. It's traveling counterclockwise. So when we evaluate this integral, when we use our right-hand rule to figure out the polarity of this integral, we're going to be doing a negative V cross B. Negative because, again, we're modeling our conductors as rotating clockwise while our field is stationary. So the reality is our field is rotating in the counterclockwise direction and our conductors are stationary, but to be able to perform this integral, to cast this in terms of our Lorentz force law, we need to model our conductors as moving and our field as stationary. So if we do this, we can see that we will have the polarity that I've indicated right here. And we'll get this expression for the voltage. It's going to be equal to the velocity of our field, r, which is r times omega by p. And if you're confused about where this omega by p comes from, please go back and review one of our first lectures where we talk about how the mechanical speed maps to the electrical frequency. Here, omega is, lowercase omega, is our electric frequency. It's the frequency of our terminal voltages, where this omega is our mechanical speed, both in radians per second. So we get this expression for our slot voltage as being R times omega by P times the magnetic field that is cutting the conductor times the length of the conductor. And so we're indicating this magnetic field that's cutting the conductor as being our magnetic field evaluated at alpha equal to the slot we're interested in. So that would be alpha 1 in this case. It could be alpha 2 in this case, alpha 3 in this case, alpha 4, alpha 5, and so on. You can see I've labeled alpha 1, 2, and 3 on our cross section right now. So that's the angular location of the conductor that we're considering. And so that would be the EMF that would be our slot voltage. That's the EMF within the slot. But in fact, each coil we're modeling as having a certain number of turns, ZQ turns, that are connected in series. Which means that our slot voltage is going to be ZQ times this E slot value that I put up there. The actual voltage in our coil side is going to be ZQ times our slot voltage. And we'll indicate this with capital UI. Great. So now what we're going to do is we're going to write out an expression for our magnetic field in terms of Fourier series components like we've previously done in recent videos. And we're going to use this to build up to a transient expression for our voltage, and then we're going to put that into phasor notation. So starting with our magnetic field, you'll recall this result from our previous videos. So I'm specifically zooming in on one harmonic component of this. So our no-load magnetic field, our magnetic loading at harmonic V. So remember, harmonic V means it's an integer multiple of the number of poles of the machine. That's different from the harmonics N. So at harmonic V, not the velocity, but harmonic V, we've got a magnitude. And then we've got the cosine of V, that's our harmonic index again, times our number of pole pairs. And then times alpha minus our angle of our rotor, minus theta mechanical. And then we have a phase angle associated with any harmonic. And as we've talked about in our previous videos, for V equal 1, this angle is 0. That's just by definition of how we indicate how we've set up our fields. And so since the cosine of a negative number is equal to the cosine of a positive number, we can rewrite this as follows. And we've put this into phasor notation, and since we flipped the sign of all of our angles, I'm going to denote this as being the conjugate of our magnetic field phasor. It is truly our magnetic field phasor when it's referenced to this negative angle over here, but in general, we take these angles to be positive, so we're going to call this the conjugate since we have a negative right there. And then we're also going to note that our theta mechanical, we're going to assume it's equal to our rotational speed times time. We're assuming that we're in some kind of steady state, and so we can express our angle as just being our speed times the time that's elapsed. And so now we have a nice result which shows us that our magnetic field at any location alpha can be expressed as a phasor in the time domain. And this is important because this is getting us to the point that we can start to talk about the voltage phasor for each of these slots in the time domain. So the voltage in coil side I, in the coil side sitting in slot I, is going to be equal to the following. And we're going back to this expression to derive that. We're going to plug in this right here to get this. And so we have this expression. We can pull a few things out here. First, we're going to flag that these first set of terms is going to be equal to the phasor of the voltage if something was located in slot 0. If a coil side is located at 0 radians off of center. And then we're going to note that this phasor is rotated based on the slot's location to determine the phasor of any arbitrary coil side at any slot. And so we see that to figure out the phasor of the voltage in any arbitrary slot, we simply rotate our U0V quantity, that is our phasor for a slot located at alpha equals 0, we rotate it clockwise by the location of the other coil side multiplied by the harmonic index. So if you want to draw the phasor for this coil side, you're going to figure out what the phasor is for a coil at alpha equals 0, and then you're going to rotate it by negative Vp times alpha 3. So let's sketch what that looks like. So I've redrawn this just for a 2D cross section, and we're going to take this 2D cross section and sketch all the phasors of each of these slots. So we'll start on with the horizontal phasor for slot 1, and then when we go to consider the phasor of slot 2 relative to the phasor of slot 1, we're going to note that slot 2 is rotated from slot 1 by alpha c radians, and so therefore its phasor should be rotated in the clockwise direction by alpha c times Vp. And assuming that all of these slots are separated alpha c radians from each other, we can continue doing this phasor star. And then we would continue to sketch this until we've drawn all the phasors. And what this is called, this diagram that we started to create here, this is called the star of slots. And the star of slots phasor diagram is a phasor diagram of the voltage induced in each coil side for a given harmonic. And it's possible that multiple slots will have the same phasor. So as you go around all your conductors, depending on how many poles you have, your magnetic conditions may repeat themselves. So we previously talked about how a 2-pole motor is kind of the fundamental motor, but if you go up to a 4-pole motor, you can visualize it as being as compressing your 2-pole motor and having it appear twice as you go from 0 to 2 pi in around your machine's air gap. And so you can imagine that if you do that, if you have a 4-pole machine or a 6-pole or an 8-pole machine, you may have multiple slots appearing with the same phase angle. And so when you draw one of these, you have to indicate what value of V you are talking about. And since our original, since this phasor right here depends on the phasor of our magnetic field, it's possible that we may not have some components in our magnetic field. Our magnetic field, if it's a pure sinusoid, will only have B delta 1, whereas if our magnetic field is a trapezoidal or a square shape, we may only have B delta when V is odd. And so if that happens, that we're missing a harmonic from our magnetic field, then we simply won't have that voltage induced. The star of slots will not exist at that frequency. And as an example, below this, I'm going to sketch a star of slots for a winding where we have multiple slots assigned to the same phasor. So in this case, we would start numbering just like we did before. 1, 2, 3. We're numbering counterclockwise. We're numbering clockwise. And this is an example of a 12-slot 4-pole motor. And how you would indicate this is that, well, the first 6 slots have distinct phasors, and now slots 7 through 12 have the same phasors as slots 1 through 6. And so we just indicate another number on here. You could also indicate this by drawing an additional phasor, an additional spoke coming off each end. I prefer just to put an additional slot number next to each arrow. And so while this may be true when we're considering V equal 1, if we were to redraw this star of slots for V equals 2 or V equals 3, they may no longer overlap. And then I want to point out a couple more things about the direction that we're labeling things. And so our sign convention in this is that our rotor rotates counterclockwise. You'll notice that your textbook goes back and forth. Sometimes the rotor rotates clockwise and sometimes it's counterclockwise. In our notes, our rotor will always rotate counterclockwise. And then we number the slots counterclockwise. So that means that we start with slot 1 here on the horizontal axis, and then we go to 2 in the counterclockwise direction, then 3, and then 4. And that is different than some of the examples in your book. And because our rotor is rotating counterclockwise, we saw from this derivation up here that our slot angle is going to, our phasor, the angle of our phasors is going to rotate clockwise. And this makes intuitive sense too. Remember that the phasor diagram indicates that this phasor assigned a 2, so I'm talking about this specific example here, this phasor is going to appear, this voltage is going to be peaking after the voltage in slot 1. That's what this diagram is telling us. It says that voltage in slot 2 will peak after voltage in slot 1, or voltage in slot 2 lags voltage in slot 1. And you can see this intuitively. First, our magnetic field is traveling this way. So first this is going to peak, and then this will peak sometime later. And then slot 3 will peak, right? So you can see that makes physical sense from your diagram, that slot 1 has its voltage phasor leading slot 2, which is leading slot 3, which is leading slot 4. And finally, we'll note that our whole phasor diagram rotates counterclockwise. This is good. This matches the phasor diagrams we talked about for three-phase quantities in a previous video. And we can see that this rotates counterclockwise because of this right here. So we can see that this whole diagram is rotating like this. Okay, so the separation between phasors of adjacent slots is denoted as alpha u, and that is called the slot angle. And alpha u is calculated as 2 pi divided by our number of slots and then multiplied by our number of poles. And this is specifically defined for the harmonic v equals 1 for our fundamental. And this is a useful tool for when you're trying to draw your star of slots. If you calculate alpha u first, then you know how to space your phasors. So I want to wrap this up by making some broader comments about how the star of slots fits into our winding design process. This tool that we've introduced right now is something that we're going to be building on as we come up with a procedure for laying out a winding. And when we design a winding, we have two primary tasks. First, we need to determine which two coil sides we should use to make up our coil. Or in other words, we need to select the pitch of our coil. We need to determine the value of YQ. And for most of our winding layouts, we're going to assume that all coils have the same pitch. So when we decide this for one coil, we've decided it for our entire winding. The second thing we have to do is figure out which coils belong to which phases and in which direction the coils should be connected to the phases. And in doing this, our goal is to create a symmetric winding. A symmetric winding means that we have, in the case of a three-phase winding, it means that each of our phases has the same magnitude of back EMF and it's separated by 120 degrees, or 2 pi by 3. And the way that we do this is that we use our star of slots. So in this example design up here, we're going to pick out coil sides to assign to windings so that we get phase U and phase V and phase W 120 degrees displaced from each other. So let's sketch what that looks like. If we pick out each of the phasors, say that we're creating phase U and we're going to pick, let's say that we group coil sides 1, 7, and then -4 and -10, and we assign this to phase U. Well, then we want phase V to lag this by 120 degrees. And as you'll see the way I've drawn this up here, that's going to be true of coil sides 3, 9, -6, and -12. And it's good that we have the same number of negative and positive numbers, because the negative number indicates that we're connecting the coil side in reverse. When you create a coil, your current has to flow one way in one side and the opposite direction the other side. So you have to have an even number of positive and negative coil sides in your phase. And then phase W needs to be another 120 degrees, or -2 pi by 3 after phase V. And you can see that we can construct that by looking at coil sides 5, 11, and -2 and -8. And this needs to be true for harmonic V equals 1. That is our fundamental. If we only have the fundamental component in our magnetizing field, we want to see that we have a perfect three-phase balanced sinusoidal back EMF, where phase U leads phase V by 120 degrees, and phase V leads phase W by 120 degrees. And you can see that looking at this star of slots, we were able to pick phasors so that this was true. It's kind of magic that this worked out at this point, but I want to comment that only certain combinations of slots, poles, and phases will allow us to do this. So if I'd given you a 13 slot design, you simply couldn't have done it. There was no way that you could have used all the coil sides to construct a winding where you had this 120 degree separation between your three phases. We'll work up to those conditions and a formal procedure for how we lay the winding out. But I want to draw your attention at this point to the bigger picture for how this all fits together. So that concludes this video. In summary, in this video we've talked about how to calculate the voltage induced in a coil side, and then we've used this to construct the star of slots. We've gone back to our fundamental definition of back EMF and then built up on this to figure out the mapping of the slots in our electric machine to the transient voltage that's created in each of those, in a coil side located in each of those slots. And we've done this to construct the star of slots phasor diagram, which we've commented is that is going to be a useful tool in laying out windings in our class. And then we had some brief comments on the overall larger picture of winding layouts.